Time, a concept that governs our daily lives and shapes our understanding of the universe, has long been a source of fascination and frustration for physicists. It's a fundamental component of our reality, yet its true nature remains elusive. Now, a groundbreaking study suggests that time may not be a fundamental element of the universe at all, but rather an illusion emerging from quantum entanglement. Published in the journal Physical Review A, this research offers a fresh perspective on one of physics' most enduring puzzles. At the heart of this revolutionary idea is quantum entanglement, a phenomenon Albert Einstein once famously called spooky action at a distance. Quantum entanglement describes a bizarre connection between particles that exists regardless of the distance separating them. The researchers suggest that it's this very connection that gives rise to our perception of time. To understand the significance of this proposal, we need to consider how time is treated in our current theories. In quantum mechanics, which describes the behavior of particles at the smallest scales, time is viewed as a fixed, external phenomenon, an unrelenting one-way flow from past to future. It remains separate from the quantum systems it measures and can only be observed through changes in external entities, like the hands of a clock. Contrast this with Einstein's theory of general relativity, which describes the behavior of larger objects like stars and galaxies. Here, time is interwoven with space in a four-dimensional fabric called spacetime. This fabric can be warped and stretched by gravity or high speeds, leading to effects like time dilation, where time passes at different rates for different observers. These conflicting views of time have left physicists at an impasse. Without reconciling this fundamental inconsistency, a coherent theory of everything, a framework to explain all the physics in the universe, remains out of reach. To address this problem of time, Copo and his colleagues turned to a theory called the Page and Wootters mechanism. First proposed in 1983, this theory suggests that time emerges for one object through its quantum entanglement with another object acting as a clock. For an unentangled system, time doesn't exist, and the system perceives the universe as frozen and unchanging. The researchers applied this mechanism to two entangled but non-interacting theoretical quantum states, a vibrating harmonic oscillator and a set of tiny magnets acting as a clock. They found that their system could be perfectly described by the Schrödinger equation, the cornerstone of quantum mechanics. However, instead of time, their version of the equation ran according to the states of the tiny magnets acting as a clock. Taking this a step further, the team repeated their calculations twice, first assuming the magnet clock was a macroscopic object, and then assuming the harmonic oscillator was macroscopic. Remarkably, their equations simplified into those for classical physics, suggesting that time's flow is a consequence of entanglement even for large-scale objects. While this research is exciting, it's important to note that other physicists have expressed caution. Despite finding the Page and Wootters mechanism intriguing, they point out that it has yet to produce anything testable. The challenge lies in shaping these theories to fit experiments and potentially modify existing quantum physics and general relativity. Despite these doubts, building ground-up theories of time from quantum mechanics may be a promising starting point. As we continue to probe the nature of time and its relationship to quantum phenomena, we may find ourselves on the brink of a new era in physics. The journey to unravel the mysteries of time is far from over, but studies like this bring us one step closer to a more complete understanding of our universe and our place within it. In the end, this research reminds us of the profound mysteries that still exist in our universe. As we push the boundaries of our knowledge, we continue to find that reality is often stranger and more beautiful than we could have imagined. The nature of time may be one of the greatest puzzles we face, but with each new discovery, we inch closer to solving it.